All right, guys, AP Environmental. This is topic 4.7. We are going to skip over 4.6. I like to put that into another part of the curriculum, so don't worry so much about 4.6. Anyway, 4.7 deals with seasons and solar radiation, so sunlight. So we're going to talk a little bit today about how the Earth rotates and how it orbits the sun and how that affects how much sunlight actually makes it to the Earth's surface, and that has a pretty big impact on living things. So before we kind of get into that, I want to make sure we understand two terms: weather and climate. We talk a lot about climate and climate change in this class. So I'll talk a lot more about that next semester as well. But these two terms are not the same thing. I want to make sure that we kind of can distinguish, between the two. Weather is just what it's like now. If you walked outside your house and just looked around and kind of had to describe what it was like, weather wise. Today is Monday, um, December 14th, and right now it's actually fairly mild. It's about 40 degrees outside. It's kind of over. I'm just looking out my window here. It's a little bit overcast. It's not rainy. It's not snowy, but it's kind of cool. So we can describe that pretty easily. When you watch TV, like we watch the news, the weatherman, will kind of give you a prediction of what the weather will be like, maybe for the next couple of days. It gets really difficult to predict weather, more than a few days down the road. It's, we can do it a little bit better now than we used to with technological advances and things like that. But, I mean, how accurate the weatherman really is, I think we all know that they're not like completely accurate all the time. So, I mean, predicting weather is, not that easy to do, but, maybe in the next couple of days you can probably do it. Um, but there's so many factors that affect it. That's why it's kind of difficult to kind of say, hey, in Crown Point, next Friday, what is it going to be like? Like we don't really know because there's so many things that influence it. Now, climate is sort of a historical perspective of weather. For example, if I said, what's the climate in Crown Point usually like in December? Most of us would say, well, in December, it's usually pretty cold. There's usually some snow, it's Christmas time, blah, blah, blah. So, like, we can say that with a great deal of accuracy because that's what it's been like in Crown Point for the last, umpteen years, right? So, climate is kind of the average weather that occurs in a region over a long period of time. Now, what we're seeing with climate change is we're experiencing climates that are drastically different from a historical perspective. We're seeing places around the world, for example, that I don't know, might be used to getting 30 or 40 inches of rain per year. They're only getting 10 inches of rain per year. So that's drastically different compared to the historical perspective of the weather and the climate that's been in that particular region. So that is what kind of gives scientists sort of some concern, about climate change, is that we're seeing climates in particular regions really changing. You know, for example, I mean, like we know that in December, it's typically cold and snowy. I mean, would it be unusual for there to be a 50 or 60-degree day in December? Yeah, that can happen. But that's kind of against the norm, right? If we have like a 3 or 4 week stretch of 60-degree weather in December in Crown Point, that would kind of be kind of strange. That's like not the normal type of thing that happens. All right, so weather and climate, make sure again we can kind of distinguish between those two things. Now, climate is driven by five different things. Okay, we're going to talk about two of them today. We've already talked about two, and there's another one that we're going to talk about more in the next lecture. But the first one is the Earth's orbit. We know that the Earth orbits around the sun, but we should also know that the Earth has a tilted axis. So as it's rotating on this tilted axis. I'll show you that more in the next couple of slides. Number two, unequal heating of the Earth by the sun. I think we were probably all aware that depending on where you're standing on the planet, you're either getting more direct sunlight or less. So not every area of the Earth is heated the same way. Some areas receive less heat, some areas receive more heat. Again, I'll show you that more in a couple slides as well. Atmospheric convection currents. We talked about air currents in the last lecture. If you don't remember what that was, or if you haven't watched that, you might want to watch that video to make sure you understand what atmospheric air currents are. Hadley cells, for example, are atmospheric convection currents. The rotation of the Earth. This deals with the Coriolis effect. Again, that was in my last video. So we've already talked about these two things, but these two things, because they kind of influence air circulation, that influences climate. All right, so we've already talked about those, so we're not going to go back into that. And the final thing is ocean currents. So we're going to talk about that more in the next lecture. So I want to focus on these first two things today. All right, so let's talk about the Earth's orbit and tilt. One thing that I do want us to understand, they usually ask you this on the AP test. The Earth's axis is tilted at a 23.5 degree angle. All right, so again, that means that, for example, if you're looking at the Earth here, it's tilted a little bit according to that particular axis. All right, so that kind of gives the Earth, a kind of a unique way as it actually orbits the sun. It's orbiting the sun on that tilted axis. So, remember, here's the equator, right? So we've got the northern hemisphere and we've got the southern hemisphere, which are north of the equator, south of the equator. So not only is the axis tilted, but that means that the equator is tilted as well. All right, so that means the northern axis sometimes faces the sun more, sometimes the southern axis faces the sun more, and that's kind of what gives us our seasons. All right, so whenever that northern axis is tilted towards the sun, we're going to have summer in the northern hemisphere. And in the southern hemisphere, we're going to have wintertime. But then just the opposite, if this southern axis is tilted more towards the sun, then the southern hemisphere is going to have its summer, and the northern hemisphere is going to have its wintertime. So here's kind of a review of that a little bit. There are a couple of terms here that I want you to be sort of familiar with. We're going to start over here on the left. Okay, this is what we call the June solstice. All right, this is the time of the year, the 365-day cycle. All right, it's the time of the year where the northern hemisphere is tilted at its maximum towards the sun. Now, usually that's around June 20th or June 21st, somewhere in there. But at that particular point, the northern hemisphere is experiencing its longest day of the year. That means there's more sunlight, in the daytime hours in the northern hemisphere than at any other point during the year. And the southern hemisphere is just the opposite, right? It's the shortest day of the year. They receive the least amount of sunlight on that particular day. But again, that's the June solstice. Now, if you move across to the other side, this is the December solstice. It's the exact opposite. All right, this is usually December 20th, December 21st, somewhere in there. But again, you'll notice that the axis in the northern hemisphere is tilted away from the sun. So this is our shortest day of the year. We receive the least amount of sunlight in the northern hemisphere. In the southern hemisphere, it's just the opposite. That axis is tilted towards the sun. They get the most amount of daily sunlight, that type of thing. All right, so remember the solstices. They take place in June and December. They are the opposite of each other. Now, the equinoxes, one of them happens in March, like around March 21st. One of them happens in September. At these two times, the sun is directly over the equator. It happens twice a year. Okay. Now, because it's directly over the equator, that means that the northern hemisphere and the southern hemisphere are receiving equal amounts of daily sunlight. So it doesn't really matter where you're at. If you're in the northern hemisphere, the southern hemisphere, you're going to receive 12 hours of light, 12 hours of darkness. All right, that's all because, again, the sun is directly over the equator. March, we typically call that spring. All right, but that's kind of like similar to the fall, which we, the September equinox, we would kind of consider it fall. All right. But, again, we kind of call it that in the northern hemisphere. In the southern hemisphere, they kind of flip it, but it's similar, again, types of climates, all because of where the sun actually is over the earth. All right. Now, the other thing that I want to talk about today that really has an impact on climate is the unequal heating of the earth. So, for example, here's our earth, right? And the sun's over here somewhere, whatever. Um, so let's just say that I don't know, let's say that we're in an equinox. Let's say it's the spring equinox or the March equinox. So the sun would be directly over the equator. And we know at different times of the year, it's at different places. But during an equinox, for example, it's directly over the equator. So we would assume that the equator would be getting the most intense amount of sunlight that there would be. In fact, I don't care what time of the year it is, because the Earth has a curved surface, all right, that equator or near that equator, that's the closest to the sun because of the curvature of the Earth. So really, I mean, the equator, is going to get the most direct amount of sunlight that there is. We call that the angle of insolation. The farther you are away from the equator, I don't care if you're going north or you're going south, the intensity of the sunlight is decreased. The distance the light has to travel to reach the earth is much greater up here in the northern hemisphere or the southern hemisphere compared to the equator. So the Earth's tilt affects the distance that sunlight has to travel to reach the surface. Hope that makes some sense. Now, another thing too that affects the heating of the Earth is surface area. For example, again at the equator, the sunlight hits the earth at a certain angle, and that's a very intense area right in that region. But if you go a little bit more north, for example, because the earth is tilted, that sunlight spreads out over a larger surface area. You notice that this surface area is a little bit larger here, near, let's say, 30 degrees north and 30 degrees south. You go even further north, right? That sunlight is dispersed even more over a certain surface area, the same thing south. So, again, as you move more north and move more south, not only is the intensity of light lower, but it spreads out more. So, you're receiving less heat in these areas north and south of the equator than if you were directly at the equator. Now, the last thing that affects heating of the earth is something called albedo. Albedo is a measurement of how much light is actually absorbed by the earth, by the surface. We'll talk about that more in a second. All right, so again, here's kind of the same thing I just talked about. You can say here we're at near the equator. That's a very intense amount of sunlight, but up in the northern hemisphere or the southern hemisphere, doesn't really matter. There's just less sunlight. All right, not that it's not going to be light, but the intensity of the light is much less because not only is it traveling a farther distance, but it's also going to be spread out over more of a surface area. It's like if you took a flashlight and shined it directly on the Earth, at the equator, and then you move that flashlight at a different angle, it's going to spread that light out a lot more. So you can actually see that pretty easily. All right, this is called the ITCZ. We talked about this a little bit in yesterday's lecture. The ITCZ, I don't want you to confuse this. It's actually a really easy concept. It's called the Intertropical Convergence Zone, and it represents a latitude. Now, one of the things that we kind of assume is that the equator, here's the equator here, right? That red line would be the equator. A lot of us assume that that line, which is at 0 degrees latitude, we assume that no matter what time of the year, no matter what time of the day, that red line, that latitude is where it's the hottest, the most intense amount of sunlight. That's it. Like that's what we think of. But it's not always true. Remember, the Earth is tilted, right, at a 23.5 degree angle. So if you go 23.5 north and 23.5 south, that range of latitudes, that kind of bluish colored area there, that's the ITCZ. And what this represents is basically the movement of heat intensity. For example, let's say today, whatever, it's December 14th. Let's just say today, you know, the most intense amount of sunlight that is reaching the earth is right here at this point with my cursor. Now you'll notice that point, not only is it on the equator, but it's also on this wavy line. Okay. Now, 3 weeks from now, the most intense amount of sunlight is no longer there. It might be up here somewhere. Okay. 3 weeks after that, it might be over here. 3 weeks after that, it might be here. And then, it changes with time. And that's all because the earth is tilted and it's rotating around the sun at that tilt or at that angle. All right, so the most intense amount of sunlight moves, and it moves along this wavy line between 23.5 and 23 north. All right, the equator is just the line that intersects that entire wave. Okay, it's at 0 degrees latitude, but the warmest area on the planet sometimes is in that area 23.5 north, sometimes 23.5 south, but it's always going to be in that area of blue at some point. So hopefully that makes a little bit of sense. All right, I want to go back to albedo real quick. Albedo, again, is kind of a measurement. It's a percentage of how much sunlight is being absorbed by a surface. It says here it's the percentage of incoming sunlight that's reflected, or we can look at it as absorbed, I guess, from a surface. So let's say, for example, that we have a kind of light colored surface. Let's say we have snow cover, right? Snow cover is kind of whitish, right? So if sunlight hits that surface, how much of that sunlight is going to be absorbed and how much of it's going to be reflected? Well, according to this picture here, a surface with a high albedo, like a white colored surface, is going to reflect 80% of that sunlight. It's going to absorb about 20%. It's going to reflect about 80%. So if something has a high albedo, it's not absorbing a lot of energy. It's reflecting a lot of that. If it has, let's say, a darker surface, like a black surface, let's say, for example, let's say you have a street that was just recently paved with asphalt or something, it's kind of black, it's a dark color. So if that sunlight hits it, it's going to absorb about 90% of that heat energy and it's going to reflect about 10%. All right, so what I want us to understand about the surface of the planet is there's a lot of different things on our surface that are reflecting and absorbing light. Typically, again, lighter colored surfaces have a higher albedo than darker surfaces. If you take a look here, for example, like fresh snow, right, has an albedo that's pretty high, right? That means that it's reflecting a lot of that energy. Whereas something that has a much darker surface has a much lower albedo. It's absorbing a lot of that energy and not reflecting a lot of it. All right. So again, it depends. All that energy that reaches the earth, you know, some of it's going to be reflected, some of it's going to be absorbed, but that depends a lot on the color of the area of the surface, and that varies obviously from place to place. All right, guys, there's a lot of essential knowledge with this topic, but I don't think it's really that difficult to understand. So again, rewatch the video if you have to, or rewatch certain parts of it if you were kind of confused. All right, guys, have a good day, and I'll talk to you soon.